about 9:30. So, hi, I'm Noah, and this is how the internet works. What is the internet? Senator Stevens was more right than he understood. At the low level, the internet is a series of tiny tubes connected in a vast network. But this is probably a better way to think about it. Quote from Ben Cerf, who is widely regarded as the father of the internet. But let's talk about one piece of information in particular. We want to see a web page, www.google.com. We're going to focus on the parts of this that interact with the internet, so we're not going to talk about keyboard interrupts or HTML and CSS rendering, but we are going to talk about how we actually get to this web page. We've opened a browser, we've typed in https://www.google.com, and we press enter. The first thing the browser needs to know is, where is www.google.com? Enter stage right, domain name system, or DNS for short. DNS is the protocol that the computer uses to figure out what IPs map to what names. The most common way to interact with DNS is the getHostByName function. Some browsers are fancy enough to write their own internal version, but the process is basically the same either way. We need to make a DNS query. So to do this, we're going to build a DNS message or packet that takes the question of what is the address or a record of www.google.com and puts it in a format that a DNS server can understand. The first section of the DNS packet is some headers. Like other protocols you may have seen, the headers include some standard data that apply to all types of packets. The ID field is an opaque number. The DNS server will include this in the reply so we know which query is being answered. The QR and opcode fields set if the packet is a query or reply and sets the type of query. The other fields set various mode flags. And the 4 count fields set the count of questions, answers, authority, and additional records. For now, we're just going to ask one question. So that will be 1, and the others will all be 0. The next section after the header is the question that we are asking. This is a bit simpler. We have the name that we're asking for, www.google.com, the type of record we're asking for, A, for address, and the class of value, which is always going to be 1 for internet. So let's put all the header and question sections together. We fill in all of the data, and we get this. This looks a little bit more intimidating, but it's the same as the symbolic breakdown we saw before. Header section, data section. We can turn bits into bytes into hexadecimal. Same thing. We have a whole bunch of bytes. We have a completed DNS message, and we're ready to hit the road. What now? We have to send that message to a DNS server to get back a reply. Your operating system will expose various APIs to ask what the system-level DNS servers are. For Windows, this is called Get Network Params. For Mac, it's called Network Services. For Linux, it's called Resolver. Usually there are multiple servers in case one is unavailable at any given time, but let's just look at the first one. 208.201.224.11, which is the main DNS server for my ISP at home. Now we know where to send our DNS query. We have an IP address we're going to send it to. We need to encode the data to send it in a way the internet will understand. We do this using 2 separate but related protocols. The Internet Protocol, as the name suggests, is the core protocol that powers the Internet. At the time it was made, networking protocols were all specific to each computer manufacturers, DEC, Honeywell, etc. So everyone that sold computers built their own network. It made setting up networks of computers of different manufacturers very difficult. So IP was developed to allow internetworking, and that became the nucleus of the Internet that we know today. These protocols are applied in a nested fashion. So DNS goes inside UDP, goes inside IP. The IP protocol lets us specify the destination IP address, which identifies the target computer, and the UDP protocol specifies the port, which indicates which program or service on that computer we want to talk to. By mutual agreement of everyone that works with DNS, we're going to use UDP port 53 for our DNS query. So the first layer on top of our DNS query is going to be the UDP data, so let's look at that header format. Most of these we aren't really concerned with, but the destination port is where we put in 53, and the source port is going to be randomly allocated by our operating system. Then on top of the UDP header, we have an IP header. This is a lot more information in it. The first is the version of the IP protocol. When people say IPv4, that's because the version is actually 4. Fun fact, there was an IPv5 very briefly. It was a voice streaming protocol developed in 1979. It didn't really go anywhere. Next are a bunch of fields that used to make sure the packet can be received correctly. Note that the IP and UDP checksums apply only to the header information and not to our data. The TTL, or time to live, gives packets a maximum lifespan. It isn't actually measured in time, but it hops between systems and is there to avoid packets being sent around in a loop forever. Eventually, the TTL will hit 0 and the packet will be dropped. The protocol field tells the receiver what kind of data is inside the IP packet for us. It will be 17, meaning UDP. The 2 addresses indicate where the packet is going and where it came from. We will use those to steer the packet to its final destination on the internet. In our case, the source address will be our local IP of this computer, and our destination address will be 208.201.224.11, which is our DNS server. So here we have our fully assembled packet, an IP header, a UDP header, and a DNS message made up of a DNS header and a DNS question. So just like we did with the DNS message, we'll convert this into bytes, and we are ready to go. There's nothing special about packets. There's nothing special about these bytes. It's just that everyone on the internet has agreed that they will parse and use these bytes in the same way so we can use them to communicate. We have an IP packet ready to send, but what are we going to send it to and how? We're going to look at a simple local network. Our computer is connected via a wired network to a switch. Switch is connected to a router, and a router is connected to a modem. In a lot of home networks, these three things will be inside one physical box, but the functions of it are still discrete. We'll ignore the modem because it mostly acts as a bridge to a similar modem at your ISP's local office, and it doesn't really interact with internet-level things. Most of us have seen network configuration like this before, an IP address and a subnet mask handed out by a DHCP server, probably from your local router. We won't go into details of DHCP, but let's talk about what these three values are used for. An IP address determines who you are on an IP network, and the other two values are used to build the route table. A route table is how your computer knows where to send packets. For a normal laptop or desktop, the route table will usually be very small, in this case just 3 entries. So let's use the route table to figure out where we're going to send this packet. We have the destination IP address at the top, and on the left we have a set of addresses that we're going to match against in a prefix way. So first we have the route for the addresses that all start with 127. 127 to 001 is the usual address for localhost, but technically everything under 127 is sent to the loopback adapter. Our target doesn't start with 127, so this row doesn't match. Next, we have the route for the local network. If we were talking to another computer on the same local network, this would let us talk to them directly instead of talking through the router. But it doesn't match, so we move on. Finally, we reach the default route. This always matches anything that isn't handled by one of the other routes. This is why some operating systems call this a default gateway. So we'll use this route. We know we're going to send our packet on ETH0 to the router at 192.168.1.1. But how do we send an IP packet on ETH0? Ethernet is the next layer down. Ethernet is the standard that defines how wired network devices talk to each other. When you see a MAC address, that's talking about Ethernet generally. Wi-Fi is a similar standard, also using MAC addresses and variants on the Ethernet data formats. But for simplicity, let's just talk about wired networks. Ethernet networks are divided into segments the same way IP networks are divided into subnets. A segment in Ethernet is defined as a series of network cards on a shared electrical connection. In the original 802.3 standard, it required every computer in the network to be connected to the same huge coax cable. Every computer would be connected to a shared wire, and they would use that to communicate. Over time, it became hard to scale that, so we introduced the idea of hubs with separate electrical connections, but shared segments. Hubs repeat everything that they get sent out all the wires they are connected to, so you still ended up with a lot of packet collisions. So over time, we moved from hubs to switches, which only send along the wires that are necessary. So far, we've had a DNS message and an IP packet. Now we have another layer, an Ethernet frame. A frame is one block of data sent on an Ethernet network from one device to another. Most of the fields are control data for the network cards on either side. The type field indicates what kind of data is inside our frame. In our case, it'll be 0800, meaning IPv4 data. You'll often see descriptions of an Ethernet frame omit the first 2 fields because they're always the same and are only really used for synchronization. The destination address determines who on the collision domain or segment should be receiving this frame, and the data field contains the IP packet we sent before. While Ethernet defines the overall network, the other standards define the actual electrical signals put onto the wire or light pulses onto the fiber optics. Most wired networks these days will be 1000 base T, otherwise known as gigabit Ethernet. So we're finally ready to build our Ethernet frame to send our DNS query to the local router, but we have a problem. The route table told us the IP of our gateway, but to send an Ethernet frame, we needed the Ethernet address, not the IP address. So we have to pause sending our frame to look up the Ethernet address for 192.168.1.1. We do this using a protocol called ARP, for Address Resolution Protocol. ARP sits between Ethernet and IP, helping to translate between hardware and network addresses. We're only going to talk about ARP for IPv4 and Ethernet, but there are other protocols for other pairs of network protocols and hardware types. For IPv6, this is generally called NDP. A basic ARP query is, whoever has IP address X, please send me your Ethernet address. For each ARP request, it has to be sent in an Ethernet frame by necessity, but it uses the broadcast Ethernet address so that everyone on the segment will receive and process the query. You'll note that there is no security here. Anyone on the segment can respond to any query, and abuse of this is called ARP poisoning. ARP packets are intentionally simple. Requests and replies use the same format, just with some fields set to 0 when they don't apply. So we're going to fill in the sender hardware address and sender protocol address using our MAC and IP. The target hardware address will be left empty since that's what we're requesting, and the target protocol address will be set to 192.168.1.1. Then we wait. ARP can take a few milliseconds as it has to get to the other computer, get decoded, figure out if it matches the query, send back a response, let the response be decoded. This is why ARP is cached very aggressively at almost every level of a network. In our case, we don't have it sitting in our local cache, so we just have to sit around and wait for an ARP reply to be sent back. But at long last, in computer terms, we get our ARP reply. We finally have all the data we need to send our DNS query. To review, we have an Ethernet frame going to the hardware address of our router. Inside that, we have an IP packet with the destination of our DNS server. Inside that is a UDP datagram for port 53, and inside that is a DNS message asking for the A record of www.google.com. This is a lot of work, and we haven't even gotten to the local router yet. So that packet is sent down the wire. Through the switch reads the destination MAC address on the Ethernet frame to know which port to send the packet to. Or if it doesn't recognize the MAC address, it just sends it to all ports and hopes that it eventually gets to the destination. Either way, somehow, eventually, it makes it to the router. The local router in our home network serves two main purposes: routing between the home network and the ISP network, and performing network address translation. Unlike the switch, it needs to decode most of the packet to do these, but let's look at them in turn. So the first thing the router is going to do is decode the Ethernet frame. It has to check that it matches the destination Ethernet address. It does, so it knows that it is the intended recipient of that frame. Then it has to decode the IP packet and check if it matches the destination IP address. It doesn't match, so it knows it needs to send it somewhere else. This works just like it did on our computer, but because it's connected to two different networks, our home network and our ISP network, the route table has an extra entry. So just like last time, we have the destination address up top, and we start at the top and try and find a prefix match. Still doesn't start with 127. Also doesn't start with 192.168.1. Also doesn't start with 172.228.34. So just like last time, we fall back to the default gateway. Here we can see it's 173.228.34.1, and we're going to use the ETH1 interface. Once the router figures out that it wants to use the ETH1 interface, it checks with the operating system on the router itself for any special policies for that network. Most home routers are set up to do a network address translation policy on their public interface. This is because the local network uses private IP addresses that are reserved for internal use. If we send our DNS query with a source IP address of 192.168.1.2, the DNS server would have no way to send the reply packet back to us. Network address translation fixes this by rewriting the packet so that the public IP and port are something that the DNS server can actually send a reply to, and it holds the translation table so that when the reply comes back, it can reverse the translation and send the packet back up to our computer. After that is finished, sending process just like before, we have to get the MAC address of the next router we're sending to. Once we have that, we make a new Ethernet frame, and we're off onto the wires again. We're going to skip over the cable or DSL modem as they're mostly transparent, but the quick version, they read Ethernet frames, and they translate them either to DOCSIS or PPOE, and they get translated back at your local ISP office. So the first router that we're going to get to on the ISP side is usually called a border router because it lives at the edge of the ISP network. So you've transitioned into the ISP at this point. Our plucky little DNS query has finally made it to the internet. Not very far, mind you. The border router for your home connection is probably only a few kilometers from your house, but still progress. So far, both hops we've taken have used relatively small route tables with default gateways for unknown destinations. This works well for small networks that are arranged in a tree or hub and spoke pattern, but as we get further into the ISP's network, it's going to start looking a little bit more like a mesh. The same process we saw earlier in our own router will repeat a few more times. Tree of regional routers in the local ISP office will sort of filter up closer and closer to the backbone connection. The ISP backbone is a set of high-speed links, usually fiber optic links, between local or regional offices of our ISP. Our little DNS query has made it up. We've finally gotten onto a backbone router. This router is plugged into a lot of high-speed links to other backbone routers run by our ISP in their other offices or their other data centers. We've got a problem, though. So far, within the regional office, we've been sort of in this tree-like structure, but we get to this backbone router, and it's not quite a full mesh. We can't always get to every other backbone router, but there's multiple paths available. How do we know where to send the packet? Enter BGP. Border Gateway Protocol is the most widely used routing protocol on the internet today. What is a routing protocol? Simplest version, it's a way for routers to share and synchronize entries in their route table. This is important because the exact shape of that mesh that we saw before is constantly changing. Hardware is coming on and offline. New links are coming online, not to mention the natural enemy of the internet, backhoes. The internet is built to automatically detect these changes and reroute packets around them. BGP does this using a gossip-based approach. Each router shares all of the routes it knows with its immediate neighbors, called peers. These peering arrangements are generally hand-coded into each router participating in BGP, so this isn't entirely self-organizing, but it allows, once the peering arrangements are set up, for automatic change detection to occur. As before in our simple route table, BGP operates on IP address prefixes. Somewhere on the global BGP mesh, there is a router that announces it controls 208.201.224/19, which is the prefix containing our DNS server. Each BGP peer announces which prefixes it wants to be the destination for, and each neighbor tracks which peers it saw every prefix from. It compares each new announcement with all its existing routes, and if the new route is better than an existing one, it gets added to the route table and sent along to all of that router's peers. In this way, each router gossips to the next about what it thinks the best routes are. It also means that every BGP router has to keep the entire worldwide route table in memory at all times. It's currently about 600,000 route entries. Before we talk more about BGP, we need to talk about autonomous system numbers. We've seen a lot of addresses so far: UDP ports, IP addresses, MAC addresses. AS numbers are how BGP handles addressing. An AS represents an entity or network operator that wants to participate in BGP. AS numbers are historically limited to 2 bytes, but there's recent moves to move to 4 bytes because we're running out of them, as we were with IPs. About 80% of the 2-byte addresses have been allocated so far. Some large companies have multiple AS numbers due to either corporate acquisitions, geographically distinct networks, logically distinct networks, but roughly speaking, you can think of an AS as equivalent to a company. Our DNS server is located in AS 7065, so each prefix that gets announced into BGP gets attached to a peer and to an AS number. I should also briefly mention IANA. It's a department of the Internet Corporation for Assigned Names and Numbers, or ICANN, which more or less administers the Internet. It handles allocating IP addresses and AS numbers through 5 regional organizations: AFRINIC for Africa, ARIN for North America, APNIC for Asia and Australia, LACNIC for Latin America and the Caribbean, RIPE for Europe, Russia, and the Middle East. These regional registries handle IP and AS allocations for each of their member countries. Okay, back to BGP. What determines the best route to something? So I said every time that it sees a new route, it compares to the existing ones, and if it's better than an existing route, it gets replaced and gossiped out through the network. So when it's determining what is better or best, it follows a set of steps. I'm skipping a couple of the weirder ones, but roughly speaking, these are the steps that it uses. Weight is an optional local value. It's configured by hand on each router if needed. It allows local network operators to prefer cheaper or more reliable links or other kinds of direct manual overrides. Local pref is similar to weight, except while weight is specific to a single router, local pref is shared by all routers within a single AS, but again, it's a manual override. AS path is the interesting one. As routes are gossiped through the network, you track which peers you heard gossiping everything through. And AS path prefers the routes with the fewer distinct ASs in their gossip path. This doesn't count actual number of network hops, it counts distinct ASs with the hope that fewer ASs is going to be a better path. Next is origin. So this prefers routes from within the same AS instead of external routes. The multi-exit discriminator, or MED, allows an AS with multiple connections to another AS to request preferential routing over one over the other. Both routes will still be considered in case one goes down, but generally it's used to prefer things like faster, newer links over older backup ones. Metric prefers routes with fewer hops across an internal network, so it's like AS path, but it's comparing router hops within the same AS instead of counting the distinct ASs. If we've gotten this far, we fall back to the oldest of the 2 routes. This helps to reduce the effective instability as new routes come online that are equivalent to old ones. And after this, there's a couple of tiebreakers just to make sure that every router that participates in BGP will always come to the same conclusion given 2 routes. A quick aside, because this tends to surprise most people, nowhere in this discussion of BGP have I mentioned authentication or authorization. That is because there isn't any. Any AS participating in BGP can advertise any routes they want. Abuse of this is called BGP hijacking, and we see public incidents every couple of years. In 2008, a Pakistani national ISP claimed that they were the correct route for all of YouTube, and yesterday, for about 15 minutes, a Swiss ISP took over Amazon, Facebook, and Apple. BGP is always running in the background, so by the time we get to our backbone router, it should already have a route in that enormous table of 600,000, so it knows where to send our DNS packet. While building the table is hideously complex and Byzantine, it works in the same way as all the other route tables we've seen. It's just a lot bigger. The DNS server is run in a different department of our ISP, so it happens to be in a different AS than where my home connection links up to the backbone, so we have to pass a couple of hops along backbone routers until we finally get to the data center containing our DNS server. But eventually, also known as about 60 milliseconds, we get the ISP's DNS server. Just like all the routers, the DNS server will have to decode the Ethernet frame, it'll decode the IP headers, and it'll check to see if it matches the destination IP address in the packet. Unlike all the previous steps, finally it matches the destination IP address, so it knows I am the correct server, I don't need to send this anywhere else, I'm going to keep decoding this packet, see what happens. So decodes the UDP header, it sees that we put UDP port 53, checks some internal operating system tables, sees I have a process listening on port 53, so it decodes the rest of the data and sends it to the process listening on port 53, which is probably bind. Now the real work can start. The DNS server unpacks the question data, sees we're asking for the A record for www.google.com. On a busy public DNS server, this would usually be cached, but for our example, we're going to say it isn't because this would be pretty boring otherwise. Our ISP's DNS server doesn't directly know the answer to our question. It doesn't have someone hard coding in what the address of google.com is because that would be out of date almost immediately. So it could just reply back saying that it doesn't know, but that wouldn't be very useful. So DNS has a mode called a recursive query. It means we're going to ask the server to go and find the answer to our question and then send it back to us. Not all servers will allow recursive queries, but ISP-level servers will allow them for their customers at least. So we're going to find the value of this DNS query from scratch. We need to start from something. The base of the DNS system are the 13 root servers. These live at 13 fixed IP addresses, although each individual IP address maps to hundreds or thousands of servers all over the world to handle the volume of queries. Root servers map top-level domains like com.net and org to TLD-level master name servers. All root servers are interchangeable, so you generally just pick one at random. Our ISP's DNS server has the hard-coded list of 13 root servers. This is called the root hint file. It's a file you can just get from IANA. It picks one of those, let's say a.rootservers.net, and it sends a new request for the A record for www.google.com, so basically the same DNS query we sent to our ISP. It sends it to a.rootservers.net. So, going to do the whole same thing. It's going to make a DNS message, wrap it in IDP, wrap it in UDP, wrap it in IP, send an Ethernet frame, send it across the network. It's going to span the whole internet, but eventually we're going to do all that same work, and our ISP DNS server is going to get a DNS reply back that looks like this. So that server, root servers, don't know the answer to our query. But what they do know is, here are the name servers responsible for com, go ask them. So we get back a whole bunch of name servers that are responsible for .com. These are the TLD level servers. Each of the root servers is run by a different organization for stability and to keep one person from owning the whole internet. But VeriSign owns .com, so they run all 13 of the .com TLD level servers. But again, they should all be interchangeable, so we pick one at random. Let's just say a.gtldservers.com. And we're going to send it the same question again. What is www.google.com? Again, it's going to tell us, I don't know, but here is the server that is responsible for google.com, go ask them. So when you register a domain name and it asks you, what are your name servers, this is where those end up. Those get registered into the TLD level name servers so that it can pick up your actual name server config. So we pick one of the ones for Google at random, and we send it the same question a third time, and finally it can respond. We've hit Google's name server, and Google's name server knows the answer to the question, what is the A record for www.google.com, and it happily sends it back to us. So remember, we've been doing 3 different DNS queries, all that same work that we saw in that basically first half of the talk. That has just happened 6 times. 3 requests, 3 replies. So our ISP's DNS server has the answer to our question at long last. It stores it in local cache, so it doesn't have to do this every time, because common DNS queries, this would get to be way overload. So it stores it in local cache, and it sends the answer back to us. DNS message it has to encode it into an answer. So again, we have a DNS header, just like we saw before, 0 question sections, 1 answer section. It will send it back over the ISP backbone, probably in the same path it took to get to the DNS server in the first place, but maybe not. It gets back to the local router. The local router checks its NAT table and sees, hey, this port was part of a NAT policy that I set on the way out, so I'm going to reverse the translation on the way back in, sends it back into the local network. It ends up getting back to our computer. Our computer decodes the packet, realizes that this is a DNS reply that was from a process, sends it back up into that process, probably our web browser, and our web browser finally has the answer to what is the IP address that we are trying to access. Remember, that's what we were doing half an hour ago. So we're finally ready to open a connection to the web server at www.google.com. DNS uses UDP inside IP, but web traffic generally uses TCP instead of UDP. The internet is a dangerous place for packets. Most packets will get to their destination, but there's always a percentage that will get dropped along the way. This is usually due to network congestion or data corruption, but with UDP there's no real recourse for this. When we sent out our DNS query, we started a timer in the background, and that if that timer expired, it would either repeat the DNS query or just tell us that it couldn't find the answer. TCP offers a more reliable stream-oriented protocol, so it builds a reliable transport on top of the unreliable internet. Packets will be resent if missing, and they'll never be delivered out of order. Like with UDP, there's a packet header. It's a bit more complicated than the UDP headers. Again, we have source and destination ports. The sequence and acknowledgement numbers are used to track the order of packets being sent and which packets have been received correctly. The window size is the number of packets that can be sent at once before waiting for an ACK. The checksum field is used to ensure that TCP headers don't get corrupted, and the offset and origin pointer fields are used to speed up decoding a bit. Options is there, but very rarely used. And finally, we have a set of 6 one-bit control flags. These are used to set the mode of the TCP packet. To establish a TCP connection, we need to complete a 3-packet interchange, often called a 3-way handshake. First, the client sends a SYN, or synchronized packet, with a random sequence number to the server. The server responds with the SYN and ACK for acknowledged flags set, with the client's random sequence number and a new sequence number for the server. And then the client responds back with a final ACK with its own sequence number +1 and the server's sequence number. So this is a negotiation that both sides will end up with each other's random sequence number, and then normal packets can proceed. TCP does reliable in-order delivery using these sequence numbers and acknowledgements. So we send a whole bunch of packets. The server acknowledges it. We send a bunch more packets. Server acknowledges. In this case, you can see we dropped somewhere between packets 15 and 20. We dropped something. So we just send whatever the server is missing. TCP has been retrofitted and upgraded more times than almost anything else on the internet. If you want to figure out how TCP works in practice, you'll have a lot of reading to do. So we have a TCP connection open. The browser can start to send data. If this was plain HTTP, we could just jump straight to requesting the web page, but hopefully these days most people are using HTTPS. This means we need to create a TLS connection before moving on. TLS means the same thing as SSL, just a name for an earlier version of TLS. That's all I need to say about that. Just like TCP creates an abstraction for reliable data streams, TLS creates an abstraction for an encrypted data stream. So the thing inside the stream doesn't need to know the details of how or why it's being encrypted, and it also allows either party to identify themselves through cryptographic proof, although usually only the server does this in the form of an HTTPS certificate. I'm not going to talk about the specifics of the cryptography involved in TLS. There's lots of great talks about them on the internet, and we'd be here all day. So I'm just going to cover the packets and messages that are involved. So we saw a TCP handshake. Just like that, there is a TLS handshake. We already have a TCP connection open, so at this point, TLS messages may not correspond directly to packets anymore. TCP automatically slices up the data stream into packets to maximize efficiency. So when I say message, it means some arbitrary number of packets that we don't know about anymore. The first message in any TLS connection is a client hello. It includes a per connection random number and a list of ciphers and TLS versions the client supports. Server then responds to that with a server hello, again includes the server random number, and picks which TLS version and cipher are going to be used. After this, it usually sends a certificate message, which is the proof of identity of the server, so proving who you are on the other end of the connection. Then it sends a server key exchange with configuration information depending on which cipher is being used, and it sends a server hello done, meaning that it's finished with this round of the handshake. Client uses the server's key data from the server key exchange message, sends its own client key exchange, finishes negotiating the required information for the cipher, and then it sends change cipher spec. So everything after the change cipher spec is going to be encrypted. After that, it sends a finished. This serves two functions. One, it says that I'm done, I'm not going to send any more messages, but it's also a failsafe in case something has gone wrong in the negotiation, because the finished message is itself encrypted, and if the other side has failed to negotiate correctly, it will be unable to decrypt the finished message and won't move on. Server does the same thing as the client, sends change cipher spec saying everything I'm going to send you will now be encrypted, sends a finished, same reason. After this, the TLS connection goes transparent, so it's just going to be wrapping HTTP, encrypting it, and then when it gets to the web server, it's going to decrypt it and hand it to the normal HTTP processing machinery. So the HTTP systems don't necessarily know about TLS after this point. Quick review, we've done a DNS query to find the IP address of www.google.com. We've established a TCP connection, then a TLS connection, and now we are ready to send an HTTP request to get our web page. HTTP is probably the piece of the journey you are most familiar with. Text-based protocol, request response, etc., just like DNS. HTTP request has three parts. The first is the status line, the verb, get, the path /, and the HTTP version 1.1. After that, you might have a header section. HTTP 1.1 only requires the host header, but there are a lot of optional headers that you'll see browsers sending for a normal request. And then after that is the request body, which for get will be empty. Once we have our connection open and our TLS request ready, off it goes. Just a reminder, it's going to be wrapped in TLS messages, wrapped in TCP packets, wrapped inside IP packets, wrapped inside Ethernet frames, and this whole pile will be shipped off to a local router where it'll follow the same process as our DNS message did. This time it's going to go a lot farther. For the DNS query, we're only going to our local ISP's DNS server. In this case, we're going to go to whichever of Google's web servers is closest to us. So probably a couple more hops over the backbone. But assuming everything has gone smoothly, we will get a response back from Google server. The first line special, again, the response protocol dictates what version we're going to be using. Then it gives a status, and then it gives the headers for the response. In this case, the only one we really care about is content length. Then a blank line, and then whatever the content is. HTTP is a generic protocol. It can handle web pages, images, sound, CSS, whatever. But in this case, the response data is going to be HTML. After the first request, there'll probably be a couple others, Google's logo, image, CSS, whatever. But for the most part, we've accomplished our goal. We've braved the internet, we've gotten packets all the way from our computer to Google, and we are rewarded with the search box we all know and love. It is important to remember that this half-hour, 33-minute discussion covers about 150 milliseconds of real time. For all its failings, the internet is remarkably fast, reliable, and resilient, even more so when you remember that most of this technology was developed in the 70s and 80s. So the final question, how does the internet work? Surprisingly well. Any questions? The question is, what is a packet? So it can mean a couple of things depending on the context. When you're talking about an Ethernet frame, in that meaning, it's a set of electrical signaling. So it's actual electrons that we put onto a wire that will be decoded to mean the same thing as you sent in the first place. When you're talking about an IP packet, it's just a series of bytes. Like I said back in the beginning, there's nothing special about those bytes. It's just that everyone has agreed that they will parse them in the same way and use them to do a thing. So Ethernet defines a way to turn bytes into electrical signals, and everyone else just agrees this is how we're going to use these bytes to do stuff. Yes? So the question is, do you send requests to all the root servers or just one? And just one. All the root servers are interchangeable. They all have exactly the same data in them. There are 13 of them. Specifically, there are 13 because that is the most that can fit in one UDP packet, and there are more than one of them for... It's hypothetically for reliability, but mostly it's because no one wanted any one organization to have complete control over internet naming. So each of those 13 root servers is run by a different group. 4 of them are directly or indirectly run by the U.S. government, but the rest are private organizations. There's a couple of non-U.S. companies in there, etc. Yes. So each of those 13 IP addresses maps. A couple of them are only in one place. Like there's a US DoD root server, which is in one place, I think somewhere in Washington. But the main root servers that everyone uses, it's one IP, but that IP maps to thousands of servers all over the world. They use a bunch of really fancy routing techniques so that it looks like you're talking to one IP address, but you're actually getting whichever of those 1,000 servers happens to be physically closest to you.
So what is your favorite free protocol analyzer?
What is my favorite free protocol analyzer? I mean, there's not very many of them, so Ethereal is, or Wireshark, whatever it's called now. Yeah. My brain still says Ethereal, but they lost that name in a trademark dispute like 5 years ago, 10 years ago. Yeah.
And what role did that play in preparing this talk?
None. Most of those protocol descriptions are just straight from the RFCs.
Okay.
So the BGP algorithm, what determines the weight and local preference?
The question is, in the BGP algorithm, what determines weight and local preference? Human operators. So they are manual overrides for when the human just says, no, I want to use this route, I promise. So, like, when there is a BGP hijack, for example, someone will just go in and manually set the weight of those announces to, like, -1 million, whatever. They're completely manual overrides, but because the whole thing is held together with duct tape and baling wire, that's used more often than we would all like.
Is the move from 2 byte to 4 byte AS numbers in BGP going to be part of all the BGP hijack?
No. Sorry, the question is, will the move to have longer AS numbers help at all with BGP hijacking? And the answer is no. It's sad. So the problem is most of the hardware that runs the internet is aging pretty fast, and it's already, people had to replace stuff. When we moved past 512,000 routes, that was the route table limit on a lot of older core routers. And so about 5 years ago, everyone had to replace all their hardware. And in order to add some kind of authentication, we'd probably have to do that again, and no one wants to spend the money. Instead, we're just adding what would be the equivalent of static firewalls around people that are bad speakers on BGP. So like that Swiss ISP, everyone that peers with them has now set up filters saying if they announce anything other than these like 3 routes, and we know which routes they are allocated, we are going to filter them. They can only announce those specific routes into our networks. And so like a couple of other known bad actors, say the entire country of Pakistan, is also just heavily restricted in sort of a ring fashion. Everyone that talks to them gets a lockdown set up.
Was this most recent Swiss incident, was it accidental or malicious?
They're all probably accidental. The Swiss one almost certainly was just a misconfiguration. The last one in 2008, they were attempting to do some hijacking internally and accidentally redistributed externally, stuff like that. That happens about every 2 to 4 years. Question? Yes.
Given that, like you said, a lot of the stack is aging, what parts do you think that like widespread IPv6 deployment will be breaking? Like running routes and stuff like that?
The question is, given that the stack is aging, what parts of this will likely be broken by IPv6? Yeah, a lot of BGP speakers are not really prepared for a massive influx of IPv6 routes. Because IPv6 doesn't need NAT, that means that people get given a lot bigger blocks of IP addresses, and then they subdivide them a lot more, so there's a possibility of a much larger route table eventually. People will just have to spend more money and get better routers. Questions? Yes?
How does it determine which Google server you're going to hit of all the ones they've got? Just time-based?
So the question is, how do you determine which Google server you're going to hit? So the first line of defense is what the DNS server gives you back, and so that will, for Google, I'm sure, engage in like a geo-analysis. So the DNS server can see which IP address the request was sent from, and so it can determine what answer to send back based on which is geographically closest. There's also a technique called BGP Anycast. Remember I said that that if 2 routes are equivalent and one is better, it'll just distribute that through the BGP network. It means that you can announce a single route in more than one place on the BGP network, and it works kind of like, if you've ever seen, like, you put, like, drops of colored oil in water and they sort of spread out and create a Voronoi diagram, that kind of thing. The BGP network works similarly because anyone that is closest to each announcement will preferentially use your announce, and everyone that is closer to someone else will use their announce. So Google announces the same IPs, the same prefixes in multiple places all over the world, and whichever you are closest to in terms of network connection, you will use automatically. So Google doesn't even have to do that. It's just sort of a hack on BGP.
One time I took the call myself, the response coming out there with 5 milliseconds.
Yep.
Anywhere I go, what kind of metric do you use?
Sorry?
What kind of metric do you use for the data might be Google.com responses about less than 5 milliseconds?
So the question is, anytime you ping google.com, the response is less than 5 milliseconds, and that's the BGP Anycast. So they have local data centers attached to almost every network in the world at this point, probably, except China, maybe. So if you did a trace route to that, you'll see it's probably something that's only going through 1 or 2 intermediary network hops. And that is why Google is so fast. They also cheat in a couple of ways. They have very liberally interpreted the TCP spec and will send data faster than they're probably supposed to, which is gross because they're breaking standards. I think they have turned off a lot of that because people were giving them a lot of grief over this, but they still are. They are correct in advocating that TCP was designed in 1970 and was designed for 1970 era network speeds, and we can handle data much faster these days. Other questions?
I've seen really complicated presentations that use BGP on a container host to do magic where suddenly all of your containers have a same IP address and are all routable.
Mm-hmm.
If you've heard of that, can you explain a little bit more on how that works and how BGP fits into that?
So the question is that the person's seen using BGP in a container setup to try to deal with container routing so that the containers can all just talk to the internet. What I talked about is called eBGP or external BGP. There's another mode called iBGP for internal BGP where you don't use the whole 600,000 global route table, but use the same algorithm for local route tables. And there are Linux daemons that will do that. There's 7 or 8 of them at this point, and so you can hook that up internally to do that same sort of routing computation, but on your local route table stuff. Any other questions? That is all I have.